Hello everybody, welcome to the channel Learn to Earn for Life.
Dear students, I will solve another problem on three-phase symmetrical faults. The problem statement is: a synchronous generator and motor rated for 30,000 kVA, 13.2 kV, and both have a subtransient reactance of 20%. The line connecting them has a reactance of 10% on the base of machine ratings. The motor is drawing 20,000 kilowatt at 0.8 power factor leading. The terminal voltage of the motor is 12.8 kilovolt. When a symmetrical three-phase fault occurs at motor terminals, find the subtransient current in generator, in motor, and at the fault point. Let us solve the problem. The equivalent circuit of the system in subtransient period for the calculation of pre-fault voltage is shown in this figure. Here the value of the voltage sources are subtransient internal voltages. Let me choose base MVA is equals to 30 MVA, base kV is equals to 13.2 kV. The pre-fault voltage at the fault point is 12.8 kilovolts. As we know that before the occurrence of the fault, the terminal voltage of the motor was 12.8 kilovolts, and itself it becomes the pre-fault voltage. Let us use this as the reference phasor per unit value of the pre-fault voltage. Pre-fault voltage in per unit, that will be equals to actual value of the voltage divided by base value. So it is 12.8 divided by 13.2 is equals to 0.97 at an angle 0 degree. And the base current IB is equals to 1000 into MVA base divided by root 3 into kV base. So IB is equals to 1000 into 30 divided by root 3 into 13.2, it is 1312 ampere. The load current IL is equals to total power divided by root 3 V cos phi at an angle of cos inverse of phi. After the substitution, we will get the load current as 1128 at an angle 36.9 degree ampere. The load current in per unit is actual value divided by base value of the current, 0.8594 at an angle 36.9 degree per unit. So there are two methods in calculating the subtransient voltages as well as currents. First one is using the Kirchhoff's laws. The first method using the Kirchhoff's laws. The subtransient voltages EG double dash and EM double dash of the figure. You can observe EG double dash and EM double dash are calculated by Kirchhoff's voltage law as shown in figure, as shown below. EG double dash is equals to 0.2 JIL plus 0.1 JIL plus VPF. So after the substitution, we will get EG double dash is equals to 0.84 at an angle 14.2 degree per unit. EM double dash is equals to VPF minus 0.2 JIL. This is written based on the circuit. Please observe the circuit carefully. Based on that, we have written this expression. So after the substitution, EM double dash will be 1.0819 at an angle minus 7.3 degree per unit. The equivalent circuit of the system on the occurrences of the three-phase fault is shown in this figure here. The subtransient fault current IF double dash at the point computed by summing up the subtransient fault current in the generator. Ig double dash and the subtransient fault current in the motor Im double dash. That is, If double dash is equals to the subtransient fault current at the generator as well as the motor. The sum of that will give you If double dash. Applying KVL in the circuit, we need to apply KVL here. So we will get 0.2 JIG double dash plus 0.1 JIG double dash is equals to EG double dash, or I can say Ig double dash is equals to EG double dash divided by 0.3 J. So on solving, we will get 2.8 at an angle minus 75.8 degree per unit. Also from the figure we can write 0.2 J Im double dash is equals to Em double dash. Im double dash is equals to Em double dash divided by 0.2 J. On solving, we will get 5.4095 at an angle minus 97.3 degree per unit. Hence, the current at the fault point If double dash is Ig double dash plus Im double dash, that is equals to 8.065 at an angle minus 90 degree. This is how we can solve the subtransient fault currents by using Kirchhoff's law. The second method is using the Thevenin's theorem. Here, the pre-fault voltage at the fault point is Vpf in per unit is 0.97 at an angle 0 degree per unit. This is the Thevenin equivalence voltage at the fault point. So we can take Vpf as V Thevenin is equals to 0.97 at an angle 0 degree per unit. We need to calculate the Z Thevenin, the Thevenin impedance. So we need to short circuit all the voltage sources in the equivalent circuit. Then we can get, after short circuiting, the equivalent diagram will become like this. So with respect to the fault point and the reference, the 0.2 J and 1 J are in series, and hence this is in parallel with 0.2 J. So Z Thevenin is equals to 0.12 J. Hence the Thevenin equivalent circuit of the system with respect to the fault point is V Thevenin in series with Z Thevenin with respect to the fault point. The equivalent circuit during the fault condition will be, on short circuiting the point F, here it will look like this during the fault, and hence the current at the fault point will be equals to If double dash is equals to V Thevenin divided by Z Thevenin will be 8.06 at an angle minus 90 degree per unit. Now we need to find the subtransient fault current in motor and generator. When the fault occurs, there is a change in the current supplied by the motor as well as generator. This change is calculated by connecting the Thevenin's voltage with reversed polarity. So this is, we need to remember, at the fault point we need to connect the Thevenin's voltage with reverse polarity. Here all the other voltage sources are replaced by short circuit. So you can observe here V Thevenin is connected here with reversed polarity minus plus at the fault point. So now we can calculate I1 as 0.97 divided by 0.2 J plus 0.1 J is equals to 3.23 at an angle minus 90 degree. I2 is equals to 0.97 divided by 0.2 J is equals to 4.85 at an angle minus 90 degree. Therefore, the subtransient fault current of the generator and motor are Ig double dash is equals to IL plus I1. On solving, after the substitution, we will get 2.8 at an angle minus 75.8 degree per unit. Im double dash is equals to I2 minus IL, that is equals to, on solving, 5.4095 at an angle minus 97.3 degree per unit. Thus, we find the currents calculated by both the methods and both the methods have given the same result. The absolute values of the currents can be obtained by multiplying the per unit values by the base current. So if we need the actual values, we need to multiply the per unit values with the base values. Subtransient fault current in the generator Ig double dash is equals to 3673.6 at an angle minus 75.85 degree ampere. Im double dash, that is subtransient fault current in the motor, is 7097.2 at an angle minus 97.3 degree ampere. Finally, the subtransient fault current at the fault point If double dash is equals to 8.065 at an angle 90 degree, that is the per unit value, is multiplied with 1312, that is the base value, will give you 10,581.3 at an angle minus 90 degree ampere. That is the actual value of the subtransient fault current at the fault point. Thank you for watching the video.